Okay, so today we are going to continue our discussion about modules, and in particular the fundamental theorem of finally generated modules over a PID. If we recall that in the last video on this subject, we proved a statement about submodules or free modules. In particular, if we recall from the last video, if M is a free R module of finite rank n. So we can think of this in terms of, if we want to look at this in terms of linear algebra, this just means that it has a quote-unquote dimension n. So it's free. It's a free R module of finite rank n, and n is a submodule of M. Then the first thing that we proved is that n is free of rank m less than or equal to n. And two, we prove that there exists a basis y1 through yn of m such that, or I'll write it out, a1 y1 through am ym is a basis of n with the condition that a1 divides a2 divides am. So this is the result that we proved last time, and we are going to use it when we prove that we can decompose finitely generated modules over a PID into a very simple form, which we're going to see in the next slide. So this is the fundamental theorem. The real meat of the theorem is in this first part, right? So this is the meat of the theorem. This is what we're going to prove today. Parts 2 and 3 are kind of just corollaries to the first part. So what does the first part say? So we have R as a PID, M is a finitely generated R module, and M is isomorphic to the direct sum of finitely many cyclic modules, cyclic R modules. So precisely this means that M is isomorphic to R to the R, right? So some free module. So this R to the R is a free R module. And then we have these cyclic modules. So we have the direct sum of R mod some principal ideal, since we are in a PID, and R, little r is non-zero, positive non-zero, and A1 through AM are elements of R that satisfy this divisibility relation, which comes from our proof of the theorem in the previous video. And then the second two propositions that come out of this talk about the torsion of a finitely generated module and the freeness of a finitely generated module. So we have M is torsion free if and only if M is free. This isn't the case with general modules over just general rings. You can have a torsion free module that isn't a free module. So this is an important result. Loosely speaking, we this part right here, this is like the torsion part. This is the torsion part of M, and this part right here is the free part. And that's what the third part says. So when we decompose a module this way, the torsion part of M are these direct sums of cyclic modules. And a module is free if it has none of this torsion piece to it. A module is a torsion module is purely torsion if that free part is equal to 0. So that's where these two ideas come into play. So to begin, we'll assume that M, of course, is finally generated, and we'll say that x1 through xn is a generating set of M with minimal cardinality. So that just means that we don't have anything kind of like extra in it, because we can always add more elements to a generating set and keep its generating properties. And we'll let Rn be the free module of rank n with basis b1 through bn. Now, there's a natural homomorphism, pi, that maps Rn, r to the n into m. That's defined by pi of b sub I is equal to x sub I for all I. This homomorphism is what many people take to be the definition of when a module is finitely generated. A module is finitely generated if and only if there's a surjection from a free module of finite rank onto um, onto your module M. Right. So this is kind of saying in terms of universal properties that um, if we have some generating set, let's just say we have 1 through n, and we have the canonical injection. So we have the free module on the set of n elements. This is the canonical injection. We can call it J. Then by our the universal property of free modules, for every map, right? So for every mapping of our set, we call this A. Any mapping from our set A into a module M. So we can think of this as kind of like selecting generators. There's a um, there's a unique homomorphism, R module homomorphism, that maps phi onto M. And if phi is surjective, then M is finitely generated. So that's kind of like the definition of when something is finitely generated. But we do see here, since we already given, we know that M is finitely generated, um, and this is a surjection. So this map that we defined, this R module homomorphism that we defined, is a surjection, since the x sub i's generate M, and we're taking the basis for R to the n, for Rn, and mapping them to basis elements of M. So it has to be finitely generated, um, or it has to be generated. Um, or it has to the map has to be a surjection. Now, by the first isomorphism theorem, we have Rn mod the kernel of pi is isomorphic to M. That's just because pi is surjective. Um, and we can apply the previous theorem, so the theorem that we stated at the beginning of the video and the one that we proved in the previous video. We can apply the theorem to when Rn is our free module and the kernel of pi is our and the kernel of pi is our submodule. So there exists a basis y1 through yn. So now we're choosing another basis, y1 through yn of Rn, such that a1 y1 through am ym is a basis of the kernel of pi with the divisibility conditions. A1 divides a2, divides all the way through to dividing am. That, as I said, this comes from our previous theorem on the submodules of free modules. So this implies that, as we know, we said before, M is isomorphic to Rn mod the kernel of pi, but we know that Rn can be written as this direct sum, since the set y1 through yn is a basis. It splits up into this kind of direct sum, and the same thing will happen for the kernel of pi, right? Since we know it's also free with a1 y1 through am ym as generators, we can also write it as this direct sum. And directness of the sum does actually guarantee that we have that this is a valid representation of r to the n and kernel of pi. Because since the intersection is trivial, because the sum is the the sum is direct, the intersection is trivial, um, because y1 through yn all are pairwise linearly independent, and are all linearly independent together because it's a basis. Now, we want to take this quotient and we want to write it in a way that uh, it mirrors more of the what we want from the theorem, right? So we wanted to do this. We're going to define a map. So a map from this direct sum into R mod um, A1, or the ideal generated by A1, all the way through R mod the ideal generated by AM, and then for the remaining factors, we are going to map them to R to the n minus m. So if you'd like, this just simply means that we have R, direct sum R, direct sum R, and this is going to be n minus m times. So we're going to take this and we're going to define it by having an element. So an element in our direct sum, so that's going to be alpha 1 y1, alpha 2 y2, all the way through alpha n yn. We're going to map that to alpha 1. So now we're projecting it into the quotient. So we're having alpha 1 mod the ideal generated by A1, so that's just alpha 1 plus the ideal generated by A1 in the quotient. So we have the quotients in each of these factors. So all these factors from 1 to m, and then the extra pieces, they just get mapped themselves. And this is clearly a surjection, because any element, B1 plus A, the ideal generated by A1, all the way through BM plus the ideal generated by AM, and then if we have BM plus 1 all the way through BN, it's clear that the element B1Y1, B2Y2, all the way through BN, YN maps to it. And now we're going to look at the kernel of the map. Just to note, this is a homomorphism. It's pretty clear that this is a homomorphism, just by the way, from how we conduct additions or sums in our quotients. And on the end right here, this just is a simple product of the direct sum. So when you sum things together, they split into individual sums quite easily. So we're going to look at the kernel of the map. Now, an element alpha 1 y1 through alpha n yn is in the kernel of this map. So this element's in the kernel if we have this equivalence here. Okay, well, what does that tell us? Well, that's going to tell us that alpha m, so right off the bat, we know that this piece right here, these have to be equal to 0. So that means alpha m plus 1 through alpha n, that has to be equal to 0. And this should be, this is a mistype, right? So we don't mean that. What that tells us is that in our original element, alpha m plus 1, y m plus 1, that's going to be equal to alpha n yn, and that's going to be equal to 0. So we know that to be in the kernel, all of these extra factors on the end that are not in a quotient, these have to be 0. Now for the remaining elements to map to 0, right? So for these guys over here, for these to be equal to 0, so for alpha I plus a sub I, for that to be equal to 0 plus a sub I, this implies that alpha I, that has to be a member or an element of the ideal generated by a sub I for all I from 1 through m. But yeah, but this implies, right? So for if alpha I is in the ideal generated by a sub I, that implies that we have this relation here, a1, a sub I, that must divide alpha I. So we can write alpha I as this kind of product here, and then we plug this back in to our original formulation, right? So what we get is the elements of the kernel are of this form: B1A1, that comes from this relation here, because we know that alpha 1, that's equal to B1, A1 for some B1 in R. So that's this kind of the relation we get, and we know that these end pieces, these have to be 0, but this is precisely this direct sum, RA1Y1 through RAMYM. Therefore, we obtain this isomorphism by the first isomorphism theorem, since the original function that we defined was this projection, and of course it's an R module homomorphism. So we have was our original domain. So we have our domain mod the kernel, right? Because we identified this. This is the kernel of our original map. This is going to be isomorphic to um, this direct sum of cyclic modules and this kind of r to the n piece on the end, and that gives us the desired result. Because if we go back to this slide, I have identified that this is actually isomorphic to R mod the ideal generated by A1 direct sum R mod the ideal generated by A2 direct sum R mod the ideal generated by AM plus or direct sum R to the n minus m. So in our original formulation, we can take R to be equal to n minus m, and we have the desired property, right? So this is our kind of torsion part, and this is our free part of our free module.